Okay, algebra students, today's lesson is all about exponential functions. So lesson 1 and lesson 2 were all about learning about the rules of exponents and solving exponential equations. So today is the next step. What do the graphs look like of the expressions we've been working with? So an exponential function has a specific form. And that form is y is equal to a times b to the power of x. Just like all the other graphs we've worked with that have had their own forms, linear, quadratic, this is no different. So this is the form that an exponential function graph will take. So if you have a look at the two completed examples below, let's have a look at example 1. They're very obvious to spot when they're written in algebraic form. So here's one. Y is equal to 3 to the power of x. Remember, we've learned that that's very different to y equals 3 times x. And the questions we're going to ask you are things like find the y-intercept and state the domain and range. So in this particular question, I've already filled the table in for you. I've given you a bunch of x values down the side and the corresponding y values. Now remember, we're focusing a lot on mental math this unit, not using our calculators. So you'll notice that to go from -2 to get the answer 1/9, that comes from doing the following substitution. So if the original function was 3 to the power of x, that means 3 to the power of -2. So we just learnt last class or the class before that is the same as saying 1 over 3 to the power of 2, which is equal to 1 over 9. So that's how I got the answer 1 over 9 for this first ordered pair. So you'll have to do that for each value of x down the side using mental math and exponent skills. Then once you've got all of those, you take each of those ordered pairs. So in this example there are 5, and then you plot them on the graph like you would with any other graphing problem, and then you put a smooth exponential curve on your graph. Now, if we look carefully and we answer the questions, the first question was what was the y-intercept? The y-intercept can be found either by looking at the table, 0, 1, or by looking at the graph. There it is, the y-intercept is 1. So the domain of this function is all real numbers because it's continuing to the right and to the left infinitely in both directions. And the range is slightly different. The range is all positive numbers, because what might not be clear from the graph here is actually that curve does not come into contact with the x-axis. It just skirts above it the whole way. And the reason I know that is because if I go back to my table and I look at the numbers, look how it goes from 9 down to 3, down to 1, then to 1/3, 1/9. If I kept going, those fractions would get smaller and smaller. 1 over 27, 1 over 81, and they would get closer and closer to 0, but they would never actually touch 0. And what that means in the world of graphing is that it would never actually touch this x-axis over here. So that is why we say the range is all positive numbers, which we have written in this class before as y can be all values greater than 0. So it doesn't touch the x-axis. So here's a new word that we've never used before, and that word is the asymptote. Now the asymptote of a graph is the value to which that graph comes really, really close, but never actually touches it. And as I just explained, the asymptote of this particular function was the x-axis. So the asymptote is the x-axis, and we write that as y equals 0. Remember, the asymptote is asking you what number does your graph get really, really close to, but never actually touch. And in this case, it is the x-axis. If you look at example 2, same idea, except this time the function is y equals 1/4 to the power of x. Remember the importance of using parentheses in this unit. So 1/4 to the power of x, if we put the value of -2 into that function, we will get 16, and so on and so on. So the y-intercept again can be seen from the table, or you can actually see it on the graph. The domain, once again, is all real numbers, And once again, in this particular example, the range is all positive numbers because, again, not very clear on the graph, but that graph is getting closer and closer to the x-axis but doesn't actually touch it, which is why the asymptote for this graph is also the x-axis, which can also be written as y equals 0. So this is our brand new word for this lesson, the asymptote. One last important thing before you guys get into practicing some of your own is for us to have a look at the difference between the two graphs in example 1 and example 2. Just take a few seconds to have a close look at the one on the left and this one here on the right. So the sentence below asks you to describe the difference that you notice about the shape of the two graphs above. So the difference in the shape between those graphs is that if you look at number 1, example number 1, or the graph on the left-hand side, it is an increasing function. So if you could please copy this as you're watching the video. It's an increasing function, which means that it starts, to use very basic language, it starts low on the left-hand side and increases rapidly towards the top right. And then if I just change colors, make it stand out, number 2, the graph on the right-hand side, is, I think you've probably guessed it by now, a decreasing function. And again, to put that into simple language, a decreasing function starts at the top left and decreases rapidly towards the bottom right. Now, if you were not able to see the graph and all you were given was the equation, so cast your eyes back up to what those equations looked like. I hope you can spot the difference between the way the two equations are written. So the two graphs look very different when you graph them. One is increasing, one is decreasing. If you didn't have the graph, the other way you could spot an increasing versus a decreasing is to look at the base of the function. So in example 1, the base is 3, and in example 2, it's a fraction, 1/4. So if your values, if we come back to the top of the page where I gave you the form of an exponential function, y is equal to a times b to the power of x. B is greater than 0, and b will never equal 1. So if b is a whole number, it's going to be an increasing function. If it's a fraction, it's going to be a decreasing function. So keep that in mind as we go through the examples that follow. Okay, no calculators, please. Let's make sure we're doing this with mental math and showing all of our working. So number 1, graph each function, find the y-intercept, and state the domain, range, and that new word that we've learned today, asymptote. So the first one is y is equal to 0.3x. So now what I'm hoping you'll recognize is that is not a whole number, that is a fraction or a decimal. It can also be written as y equals 3/10 to the power of x. So if you look back at your notes, you should now see that that is going to be a decreasing function, just like example number 2 up here. So if we fill in the values, starting with x is equal to -2. I'm going to show my working for this one. It's going to look like this. Y is equal to 3/10, all raised to the power of -2. So now it's time to use the rules that we've learnt in the last couple of lessons. We're going to raise everything that's inside that bracket to the power that is outside the bracket. So it ends up being 3 to the power of -2/10 to the power of -2. We've learned that if we have a negative exponent, if we take that and put it in its reciprocal position, the exponent will become positive. So that line can be rewritten with the 10 on the top, to the positive 2, and the 3 on the bottom to the positive 2, and that simplifies to 100 over 9. No calculators, using mental math and exponent rules. So if I go back into my table, when x is negative 2, y is equal to 100 over 9, which could also be written as a mixed number, 11 and 1/9. Now you would do the same for each of these numbers. If x were negative 1, if you just follow your working from the previous example, that's pretty simple to do. It ends up being 10 over 3, which can be written as then simply 3 and 1/3. Next one, when x is 0, we learned that anything that is raised to the power of 0 always equals 1. When x is 1, that's a simple one, y will just be 3/10, and when x is 2, it'll just be positive 9 over 100. So those are not the easiest values to graph, but we're going to go over now, and we're going to take each of those points, 1, 2, 3, 4, 5, and we're going to put them onto our graph. So here we go. So if this is negative 1, here's negative 2, negative 1, and we have 1, 2, and 3. And I think if we go up in 2s, so we've got 0, 2, 4, 6, 8, 10, 12, and so on. So there's our graph. Okay, change colors. When x is negative 2, y is 11 and 1/9. So negative 2, 11 and 1/9 is approximately there, closer to 12 than it is to 10. When x is negative 1, y is 3 1/3, just below the 4. When x is 0, y is 1. So there's my y-intercept. When x is 1, y is 3/10, so above the y-axis, not touching the y-axis. When x is 2, y is 9 over 100, a small decimal but still above 0. And if we continued, you would see those points would get closer and closer to the x-axis but wouldn't actually touch them. Now draw as smooth a curve as you possibly can through those points. Yikes. Have arrowheads on both ends, and there we have a decreasing function. The domain would be all real numbers. My range this time, similar to the examples above, it's all y values that are above the x-axis. So y will be greater than but not equal to 0. My y-intercept could come from the table, which I'm putting stars next to right here, which is 0, 1, or I could have seen that from the graph. And lastly, our new term for today is the asymptote. So the asymptote is the value to which the graph gets super, super close but never actually touches. And in this case, that is either y equals 0, or you can also write it as x-axis. I'll accept both of those answers. Another new skill that we have to incorporate, you guys, is you have to put a dotted line where your asymptote is. So I'm going to try and really exaggerate this with my orange marker here. Here is the asymptote going along the x-axis. So my asymptote is the orange line, dotted line. And that's it. That's how these questions work. So the next couple I hope will go a little bit faster because you guys now get the idea. Just another reminder, no calculators, mental math. Okay, turn the page. Next one. Y is equal to 2 to the power of x plus 1. Have a quick look at the base. It's not a fraction, it's a whole number, so I know before I draw my graph that I should be drawing an increasing function. So the first value I have to substitute is negative 2. So I'm just going to go over here to show my working. Y is equal to 2 to the power of negative 2 plus 1. Now, if I want to make an exponent positive, I put it in its reciprocal position. So 2 to the power of negative 2 becomes 1 over 2 to the power of 2 plus 1. So y is equal to 1/4 or 1/4 plus 1, which is quite simply 1 1/4. So that is how I'm going to go and put that value in there. So the rest of them, just to save a bit of time, I'm just going to fill in the answers, but you'll have to do the working to find the answers to all of these. The next one comes out as 1 1/2. Now be careful with 0, because otherwise we all fall into the trap. Anything to the power of 0 is always equal to 1. Yes, but remember in this case that 0 is going to go into this x, which means 2 to the power of 0 is 1. That's correct. But then we still have to add the 1 afterwards. And 1 plus 1 is actually 2. So please be careful about falling into that trap. If we put a 1 in place of that x, we end up with 2 to the power of 1, which is 2, plus 1 is 3, and 2 to the power of 2 is 4, plus 1 is 5. So those are my values. Those are my coordinates, 1, 2, 3, 4, 5. So now I'm going to go over to my graph, and I'm going to, as neatly as possible, try to sketch that function. So I've got 1, 2, 3 here, -1, -2, -3 on the x-axis. And then once again, I'm going up in 2s on the y-axis. 10, 12, that should be about enough. Okay, when x is -2, y is 1 and 1/4. So -2, 1 and 1/4, so just above 1. When x is -1, it's 1 and 1/2, closer to 2. When x is 0, y is 2, so there's my y-intercept. When x is 1, y is 3, and when x is 2, y is 5. So I should see a curve, an increasing function, as smoothly as possible. Connect those points, arrows on either end. Now we've got to be careful with this one. I hope you can see that this function is slightly higher above the x-axis than the ones we were doing previously, and the ones in the examples right at the very top. So let's see why that is the case. So let's begin with the domain. Good news, it's still all reals for now. The y-intercept is 0, 2. But the asymptote and the range are slightly different. And to figure that out, you need to go back to the table. So let's go down to the number 5 in the table, which is the highest value we have. And if we work backwards, you'll see the numbers get smaller and smaller, from 5 to 3, 3 to 2, 2 to 1.5, 1 and 1/4. So this time the number is getting smaller and smaller and closer to 1, not to 0 this time. Because if we kept going, it would be 1.5, 1 and 1/4, 1 and 1/8, 1 and 1/16, and so on and so on. So it would be just higher than 1 every time. It would get closer and closer to 1, which means this time my asymptote is not the x-axis. It's not y equals 0. It's y equals 1. So my graph is getting closer and closer to the value of 1. So on my graph, I have to put a dotted line to show my asymptote, just like I did on the previous page. My asymptote is the value to which my curve gets super close but never actually touches. My asymptote is obviously affects my range, so my range is all positive values for y as long as they are greater than 1. And remember, I figure that out by looking at my table, and I try and figure out which number I get really close to but never actually touch. So that's going to be the first part of your homework this evening, is filling out tables of values and drawing accompanying graphs. The second part of your homework will go a little bit faster, because it's not necessary to draw graphs for these, because if you look at the next title, it says identifying exponential behavior. And what that means is, you guys, is looking at a set of data in a table and deciding whether or not it's going to be exponential. Remember, we've seen tables of linear behavior, quadratic behavior, so now we need to be able to identify exponential behavior. And the way to do that, obviously there's a couple of ways. The first way is I give you a table and you have to look for a pattern. And the second way is to actually graph the data, and then you'll see quite clearly that it will have characteristics of exponential behavior. But if we can avoid drawing the graph, which is pretty time consuming, that would be great if we could just find a pattern. So let's have a look at this example that's done. You're looking for domain values that increase by regular intervals. So in this worked example, if you look carefully, the x values go up in regular repeated intervals. So each time 2 is being added, plus 2, plus 2, plus 2 each time. Then what you're looking for is with your range values, not to just go up in a regular interval, but in a regular or a common ratio. And the common ratio in this table is every single number is multiplied by 1/2. 64 times a half is 32. 32 times a half is 16, and so on and so on. If you can confirm this in a table, then without graphing it, you can say, yep, that is exhibiting exponential behavior. So let's practice a few in the exercises that follow. Determine whether the set of data below displays exponential behavior. So we're simply going to say yes or no, but we are going to show our work for finding a common ratio. You can eliminate, can you cross out this instruction that says graph each function using a scatter plot on your calculator? That won't be necessary. So let's have a look at the first one. If I check my domain values, it's plus 1, plus 1, plus 1. So far so good. Now I have to find a common ratio. Look at the instruction here, show work for a common ratio. So I literally just show the arrows, what I've been trying to multiply by. To get from 5 to 10, I multiply by 2. To get from 10 to 15, I multiply by 1.5. So immediately I can see that this is not the same ratio. So my answer to this question is nope. It does not display exponential behavior. That's it. Let's do the next few. These should go pretty quickly. Number 2, is it displaying exponential behavior? First we check the domain values. Plus 1, plus 1, plus 1. So yes, so far so good. And now I test for a common ratio. To get from 3 to 9, I times by 3. 9 to 27 times by 3, and 27 to 81 is times by 3. So I simply circle yes. I have shown work for my common ratio. If I was to sketch this, it would look very, very roughly something like this. And the reason I know it would be an increasing function is because the number I'm multiplying by each time is a whole number and not a fraction. Let's have a look at number 3. If I check my domain first, I go up, I add 2, and add 2. Great. And then here, I don't want to see any division, you guys. We're looking for a common ratio, a number that you multiply by each time. So to get from 32 to 16, you would times by 1/2. To get from 16 to 8, you would times by 1/2. And to get from 8 to 4, you times by 1/2. So I've shown my work for a common ratio. This does exhibit, yes, exponential behavior. And because in this one, I am now multiplying by a fraction each time, you will notice if we were graphing it, it would look something like this. It would be a decreasing function because I'm not multiplying by a whole number. And then last but not least, let's check this one out. My domain values, plus 1, plus 1, plus 1, and plus 1. Good. Now to get from each of these, no calculators. Remember, we're looking for a common ratio. To get from 1/3 to 1/9, you would multiply by 1/3. 1/9 to 1/27th, 1/27th to 1/81. Oops, you would multiply by 1/3 and multiply by 1/3. So yes, here's my common ratio work. The answer is yes, and very roughly, because again I was multiplying by a fraction, if we were graphing it, it would give us decreasing function behavior characteristics in the graph. And that's it. So 2 parts to today's lesson: identifying exponential behavior, showing work for a common ratio, and the first half of the lesson learning how to graph an exponential function and learning a new term, the word asymptote. So review these notes and get started on the homework for today's lesson, which is listed on the unit planner.